Matthias is going to talking about crowdsourced citizens weather stations.
What is started?
Yes, I'm Jonas. I'm from Bochum. I'm at the Bochum Urban Climate Lab. I'm a master's student there. And I will talk about why is it moving that way? I'll be talking about a consistent global database of crowdsourced cities and weather station data to be used for in-depth urban weather and climate analysis. So why even do this? So crowd weather stations are already very widely used in many different types of studies and have shown to be a valuable source for many different parameters. So there's been studies on temperature, wind speed, atmospheric pressure, but also precipitation. And all of them have used these stations at some point, but there are many challenges to using them. So you have to first acquire all the data, manage all the metadata, and also quality control them, since they're not in a controlled environment and you don't really know how they're set up or what other issues there are, and you kind of have to keep them consistent, manage all the data to be, in the end, able to work with also longer time periods. So what we did was set up many scan regions around the world, basically city selections, to kind of look for those cities and weather stations. So we combined two data providers. One was NetAtmo, that was shown over here, these small stations, and also Mesonet, which allows access to more stations. So all of those areas around the world are searched for those type of stations. As you can see, the global north is overrepresented again, and only a few areas are in the south. So how do we keep the database up to date? Yeah, we have these 257 regions with the two data providers as shown before. And then we also connect those with the Global Human Settlement Layer Urban Center database, basically adding more information to all those cities, and do all of those scans on a bi-weekly basis, because as you can imagine, those type of stations are very dynamic. There are new stations coming up, others are going away, and then we have to kind of classify them as moved since they change position or similar. We also add additional metadata information. As you can already see, the global map of local climate zones is added. On the one hand, the underlying pixel, but also in a radius of 250 meters, the modal value basically, and value for how homogeneous the setting is, whether there's many different LCZs in this small area. Another metric is the distance from the coast that is added. And currently there are more than 6 billion hourly temperature observations from those stations in the database. So why do we do all of this effort to kind of track them, see where they go? So this is from 2019 to 2023 for Paris, all CWS that moved somewhere. And if we would just take the 2019 image, we would miss on many, many new stations. And since they moved, we would have a completely wrong position, since they are sold, the owner moves, or other effects. So how do we take care of that much data and make it kind of accessible and usable for us? So it's all stored in a Postgres database combined with a timescale extension, which basically provides time series support for Postgres with more functions, aggregating, gap filling, and this type of stuff. And we can already do some analysis in the database without having to load all the data, because it's faster than doing this in R or Python. It's faster doing this directly in the database. But the selling point is basically the partitioning. If we have some data, we can just insert it in a table and it distributes it to child tables. So this was one timestamp, this is the next one, and it goes into a different one. So when we query now, we can select the time frame and it just needs to scan these child tables. And the third one would already be excluded, so it's faster. What we also implemented in the database is the quality control part. So all of the 6.5 billion data points are quality controlled with the CrowdQC Plus package developed by Daniel Fenner. And as you can see in the plot, temperatures go up to 55 degrees in the raw. Some are very consistent, and we kind of have to remove those. And after quality control, it becomes much more of a graph you expect. Of course, stations are removed, but the quality is increased. So what do we actually have now? So there are over 300,000 CWS in the database for now. And as you can see, 61,000 of them moved. So it's very, very dynamic. So it's essential to keep track of this. And yeah, 3.4 billion remains after quality control to the level I showed earlier. So quite a lot is removed there. Yeah, we've already utilized this in many different studies, mostly on a per city basis, but I want to highlight Daniel's presentation that was yesterday for the first time, basically utilizing the entire database in all cities in there. And of course, there are many more in preparation. The latest one being my master's thesis I just submitted a week ago, looking into urban heat advection using these stations to kind of find out what the effect of UHA is on the spatial pattern, basically, of the urban heat island. For now, advection is mostly considered as a process of the urban boundary layer, but also in the urban canopy layers can lead to underestimation of the exposure to urban heat in certain areas we're not considering. Previous studies investigated the effect on rural weather stations. So if you only have one rural reference and that's located downwind and all the heat from the city is advected towards it, is it truly rural? So that was investigated, but also using models or also using CWS for London, the urban canopy layer, urban heat advection effect was analyzed there. So first came up with kind of a theoretical concept. So wind is approaching an idealized concentric city from the left and it brings cooler air towards the city compared to like the mean pattern. This effect decreases towards the city center, where at some point there's neither cooling nor warming. But then on the downwind side of the city, in this case, right, there's warming provided by hot air being transported from the hotter city center downwind, up to a point where there's no more effect visible in natural surroundings. Yeah, there are individual situations with such strong advection. Those are two cases left for Paris and the right one for Berlin for 6 hours average. And the arrow indicates the wind direction, and you can see that the urban heat island intensity kind of follows this arrow. So there's definitely heat advected downwind in this direction. But the question is basically, is it always like this, or are there just a handful of situations that show this strong heat advection? So I had a look at 4 years of data, basically from 2019 to 2022. And in the top row, you basically see the average urban heat island pattern per wind direction, basically 4 sectors, and the arrows again indicate the wind direction. And you can already see that depending on the wind direction, the intensity varies. So with southwesterly winds, the intensity is lower than with northeasterly winds. And to kind of compensate for that, I scaled it, removing the median and scaling it to the interquartile range to kind of be able to compare them. This is the middle row, so there's no unit in Kelvin there anymore. And then I basically wanted to look how it compares to the mean spatial pattern having all directions together. And this is basically the bottom row, seeing that with northeasterly winds, the southwesterly areas are warmer than the average pattern, and this applies to all other cases as well. And I also did this for Berlin with a similar result here. Yeah, then the next question basically is, how does wind speed influence this? Of course, if there's no wind, there's likely no advection. So with 0 meters per second class, there was no significant difference between the upwind and the downwind condition. And above 7 meters per second wind speed, there also wasn't any effect visible. And you can see this pattern that there's a maximum at between 3 and 4 meters per second wind speed. And on average for Paris, the effect is 0.7 Kelvin, and with a 95% quantile, it reaches up to 1.9, but individual stations show values up to 3.1 Kelvin and a little lower for Berlin. where it reaches only up to 2.8 Kelvin and 1.5 Kelvin in the 95 percentile. Yeah, to conclude, first the database, so it still has huge potential, huge amounts of data there, and further studies can be conducted, and it's constantly growing. We get new data every month, a couple million rows, and so longer time series become available that have this consistent metadata and are tracked. And many of the cities have not yet been analyzed, only a handful, and with global analysis, we're just at the beginning. So there's still a huge potential. And yeah, with the urban heat advection analysis, I did this for Paris and Berlin. The workflow is set up to work for any city in the database, so we can have a look at other cities, maybe coastal cities, not idealized concentric cities, or cities in a more complex terrain than mostly flat. And in the end, how does it interact with the urban boundary layer? Does advection in the canopy layer always appear when it's visible in the boundary layer, or vice versa? And how do they interact? Finally, I want to make a call for any contributions. We're happy to work together, share the data. So if you're working on a city we have and kind of need a dense network of observations, please reach out to us. We're very happy to work together and share the data. Thank you very much.
Thanks, Jonas, for this nice insight of Lesatmo and the prereq, what needs to be done to get good quality data.